Imagine a garden sprinkler rotating lazily across your lawn. Now envision it ejecting perfectly straight streams of water that refuse to follow its spin, streams that remain utterly straight despite the motion beneath them. This defies physical law, seemingly impossible. Yet, precisely this defiance was observed in reality. In November 2025, astronomers captured images of comet 3I Atlas, displaying this very phenomenon. The comet completes a rotation every 16 hours, yet its expansive jets stretch for over 1 million kilometers across space in fixed, unwavering lines. There is no trace of the spiraling pattern or smearing effect expected from such rotation. The observed behavior defies our current understanding of celestial mechanics. Conventional, natural explanations for such jets appear to be failing, one by one, leaving a profound mystery. Could these not be simple gas vents erupting from the comet's nucleus? Might they instead represent controlled thrusters aboard an interstellar probe? This speculation demands consideration. What follows could fundamentally alter our understanding of visitors from the cosmic depths. Let us begin by examining the core enigma itself. Something profoundly counterintuitive is occurring right now, 400 million kilometers away from your location. On November 8th and 9th of 2025, 3 independent imaging teams recorded photographs of comet 3I Atlas. The images and the phenomenon they reveal challenge established scientific expectations. Christian Nebling and Gerald Buchner, working from Germany, stacked their long-exposure photographs. Simultaneously, Michael Jaeger, Gerald Riemann, and Rolando Lagustri Prosperi conducted observations from Austria and Italy. Crucially, all 3 distinct teams witnessed the identical, baffling sight. The comet's jets appeared unnervingly sharp and straight, utterly uncompromised by its 16-hour rotation cycle.
The 12th anomaly identified within the 3EIT Atlas system has captivated astronomers since its discovery. Far stranger than its predecessors, neither the 1st, 2nd, 5th, nor 8th anomaly, this particular object has continuously challenged scientific understanding with each new revelation. The current enigma, however, may prove the most perplexing, yet a failure to blur. If these observed jets are genuine phenomena, and if they truly maintain fixed positions relative to the comet's nucleus despite its rotation, then fundamental principles governing comets or perhaps the nature of 3EIT Atlas itself require reevaluation. Scientists have historically presumed that even the most exotic interstellar travelers adhere to the bedrock laws of physics. Gas escapes and disperses. Celestial bodies spin. Rotation combined with outgassing should invariably produce distinct spiral patterns or elongated streaks. Yet what if these established assumptions only apply to naturally occurring objects? Could the rules governing gas expulsion differ fundamentally when the object in question was constructed rather than formed organically? Delving into the quantitative breakdown, physics that should create a smear. Numbers offer an impartial perspective, indifferent to theoretical frameworks. When volatile substances sublimate from a comet's surface, when frozen carbon dioxide or water ice transitions directly into gas without becoming liquid, the resulting molecules are propelled outward at a characteristic velocity. For typical cometary volatiles, this thermal velocity is approximately 400 meters per second.
While unremarkable when compared to velocities found in space or even those of bullets, this speed remains consistent, dependable, and readily measurable. Applying this established speed to the jets emanating from 3I Atlas reveals an extraordinary scale. These features extend for roughly 1 million kilometers from the comet's central body. The calculation for gas traversing this immense distance proves surprisingly simple. 1 million kilometers equates to 1 billion meters. Dividing this by the velocity of 400 meters per second yields 2.5 million seconds, approximately 29 days of uninterrupted travel from the comet's surface to the furthest visible tip of its jets. The straightforward timeline immediately reveals the core problem. During those 29 days, how many full rotations does the comet nucleus itself complete? Given its spin period of 16.16 hours, translating to roughly 1.5 rotations per day, the nucleus would spin approximately 43 times over the journey's duration. 43 complete revolutions occur while gas streams outward to form what appear to be straight jets. Every 16 hours, any active vent on the surface sweeps completely around, rotating through 360 degrees and pointing in every conceivable direction relative to the distant stars. Logically, the gas emitted should inherit this sweeping motion, tracing out a spiral pattern, much like the swirl left by cream stirred into a cup of coffee. Yet this is precisely what astronomers do not observe. High-resolution images consistently reveal linear, columnated jets that maintain a remarkably consistent orientation for their entire 1 million kilometer length. Imagine for a moment, standing on the surface of 3I Atlas at an active vent. During the 29 days it takes for the gas you exhale to reach the edge of visibility, you would complete 43 pirouettes on the spinning nucleus. Your breath should theoretically form a vast, multiple-layer spiral disk around you, wound 43 times like thread on a spool. Instead, observations show it forms a laser-like straight line, projecting towards a fixed direction in space, completely disregarding the constant spin of the platform beneath your feet. This stark contradiction between expectation and observation forms the enduring puzzle of these seemingly straight jets. This description does not align with established behavior of gases, nor does it match the operation of rotating sources. This discrepancy holds true for every validated observational model of cometary activity. Perhaps the calculated velocity is inaccurate. Alternatively, some unknown process could accelerate the gas far beyond 400 meters per second.
Such acceleration would shorten travel time and decrease the number of rotations occurring during transit. Even doubling the velocity to 800 meters per second results in approximately 14 or 15 rotations. The gas would still trace a spiral pattern and remain smeared. Achieving a negligible rotation count would require velocities approaching tens of thousands of meters per second. At that point, the process ceases to involve sublimation. Instead, it describes explosive decompression, or rocket-like exhaust, phenomena belonging to an entirely different category. The audience must comprehend this is not a trivial inconsistency. It is not mere measurement noise or observational uncertainty. The underlying physics are as fundamental as gravity itself. When a spinning body emits gas, the gas inherently traces the path of its rotation. When 3I Atlas spins 43 times while emitting these jets, the resulting gas structure should display 43 distinct spirals. It does not. The jets maintain a fixed orientation despite the rotation. Some mechanism actively compensates for the spin. If natural comet physics cannot produce this effect, then what force could? This leads us to Part 3, the history of 3I Atlas's anomalies. Before proceeding further, it is essential to understand that 3I Atlas has exhibited strange characteristics since its very first observations. This situation does not stem from a single anomalous measurement sparking unfounded speculation. This phenomenon presents itself as a sequence of enigmas piling up like evidence at a crime scene. The object was identified in the year 2024 and designated C/2024 S1, marking it as the first interstellar comet detected following Oumuamua and 2I Borisov. Its path immediately signified an outsider from beyond our solar system, tracing a hyperbolic trajectory originating from the immense voids between stars and destined to return there after a fleeting passage through our cosmic neighborhood. From its initial observation, something fundamentally felt amiss. Early measurements registered non-gravitational acceleration, subtle deviations in its course inexplicable by solar gravity alone. In cometary studies, such behavior typically arises from outgassing, where expelled material creates a minute thrust, nudging the nucleus away from a purely gravitational course. However, the strength and direction of 3I Atlas's acceleration diverged from established models. It proved more forceful than anticipated for its observed luminosity, hinting either at exceptionally efficient outgassing or perhaps an alternative force at play. This constituted Anomaly 1. Subsequently, photometric data revealed puzzling brightness fluctuations, the variations in its light output as it rotated and journeyed through space. Comets generally exhibit predictable light patterns contingent upon their dimensions, morphology, and surface characteristics.
3I Atlas displayed fluctuations inconsistent with conventional models, suggesting reflectivity shifts indicative of an unusual surface composition or geometric structure. This formed Anomaly 2. Spectroscopic analysis further uncovered compositional irregularities, revealing peculiarities in the object's chemical makeup.
The object's alignment concerning the solar system's ecliptic plane revealed configurations many deemed suspicious. Furthermore, its observed thermal radiation failed to align precisely with established theoretical models. Each subsequent observation layered additional strangeness onto the mystery, strengthening doubts about whether 3I Atlas truly belonged alongside conventional comets. By the time November 2025 arrived, the catalog of peculiarities numbered 11 distinct features, collectively suggesting something profoundly anomalous. Then, the 12th anomaly surfaced: jets that defied blurring during rotation, maintaining fixed orientations contrary to expectations. While the initial 11 anomalies had sparked questions, this 12th finding might yield answers, or at least significantly narrow the possibilities towards something truly extraordinary. For once sufficient natural explanations are exhaustively considered and eliminated, what remains, however improbable, merits serious scientific attention. Even if the remaining possibility sounds fantastical, it must be acknowledged. Considering natural explanations, the first contender involves crater geometry and shadowed ice deposits. It is fair to grant these conventional explanations due consideration. Leaping directly to exotic conclusions without thoroughly exploring standard possibilities constitutes poor science and unwarranted skepticism. The initial natural explanation capable of accounting for these fixed jet orientations hinges on geometry. Specifically, it concerns the configuration of the surface terrain and how solar illumination interacts with ice concealed beneath the surface.
Imagine a comet nucleus sculpted into ancient collisions into a rugged, cratered landscape of peaks, valleys, and deep shadowed hollows. Within this complex terrain, volatile ices, such as carbon dioxide or other frozen gases, might be trapped, not spread evenly across the surface, but confined to specific, shaded locations. These icy pockets could reside at the bases of craters or in permanently shadowed regions, only glimpsing sunlight when the comet's orientation aligns perfectly. As the comet rotates, these ice reservoirs typically remain in perpetual cold, inert and frozen. But upon each precise rotation that brings them into direct sunlight, they undergo rapid sublimation. This sudden phase change releases a powerful burst of gas. This pulsed-out gassing mechanism could, in theory, eject discrete clumps of material rather than forming a continuous stream. Picture beads strung together, individual puffs separated by empty space. The comet rotates approximately every 16.16 hours. If an ice pocket receives sunlight only once per rotation, it generates one distinct puff of gas every 16.16 hours. Traveling at roughly 400 meters per second, each puff races outward for approximately 23,270 kilometers before the next pulse occurs. Over a distance exceeding 1 million kilometers, this process would create roughly 43 such clumps, like peas in a pod, spaced at regular intervals along the comet's path. When capturing multiple exposures over several hours, these separate clumps can blend together in the imagery, creating the illusion of a continuous, straight jet. The gas puffs exhibit a striking directional consistency because each burst was emitted when the source vent faced the same solar orientation, despite the nucleus rotating between releases. This alignment ensures every puff follows nearly identical trajectories, collectively forming a columnated structure that appears fixed against the sky. This mechanism is both ingenious and physically sound. It aligns with established observations of cometary activity influenced by complex surface features. Numerous cometary nuclei, characterized by rugged topography, including craters, cliffs, and areas with diverse surface properties, demonstrate this phenomenon.
The Rosanna mission's exploration of Comet 67P Churyumov-Gerasimenko provided a definitive example, revealing terrain-controlled outgassing. Specific regions activated only under precise solar illumination angles. The spacecraft directly witnessed jets activating and deactivating cyclically with rotation, proving shadowing and surface geometry governed the timing and location of sublimation. If such terrain dynamics operate effectively on 67P, why not on 3I Atlas? The underlying mathematics of the pulsed outgassing model are clear and experimentally verifiable. By knowing the nucleus's rotation period, estimating the gas velocity, and measuring the jet's length, one can calculate the expected number of discrete puffs and their precise spacing. High-resolution imagery with sufficient clarity should detect this potential clumpy structure. Each puff would manifest as a distinct, brighter segment separated by fainter voids, with the spacing matching the calculated distance traveled during each rotation period. Should future observations confirm this clumpy structure exhibiting the predicted spacing, the crater geometry model would emerge as the winner. It offers a natural explanation validated by its testable predictions, precisely the process fundamental to scientific progress. However, a significant challenge arises. This model proves convincingly effective only for jets directed towards the sun, where direct illumination can initiate the sublimation process even within shadowed areas. The observations made on the 8th of November, however, revealed jets extending in various orientations, including features clearly pointing away from the sun, the so-called anti-solar jets. Here, direct sunlight cannot be the triggering mechanism. One could propose explanations such as reflected light, sunlight bouncing off other sections of the nucleus to illuminate these shadowed anti-solar regions. Alternatively, one might suggest thermal lag, where some shadowed areas remain warm enough to sublimate due to lingering heat. While these ideas represent potential refinements to the model, each added condition makes the explanation increasingly complex and less elegant. Reflected light in particular presents a significant limitation. When sunlight strikes a surface and bounces off, the majority of the energy is absorbed rather than reflected. The light that does reflect is diffused and scattered in numerous directions, its intensity diminishing sharply with distance. For reflected light alone to trigger sufficient sublimation within deeply shadowed craters facing away from the sun, the reflecting surface would need to be exceptionally close, large, and possess very high reflectivity. While ice can be reflective, the surfaces of comets are typically dark, coated in organic compounds that are strong absorbers rather than efficient reflectors.
Achieving enough reflected illumination to drive substantial outgassing in these anti-solar directions demands a very specific combination of geometry and surface properties, conditions that may not consistently exist on the comet. While a definitive mechanism remains speculative without detailed surface maps of the 3 Atlas comets, thermal lag presents a more plausible explanation. This phenomenon involves certain areas on a rotating comet nucleus retaining heat after moving into shadow, enabling continued sublimation for several hours based on stored thermal energy.
This behavior has been observed on other comets and is well represented in thermal physical computer simulations. However, thermal lag typically sustains outgassing only for a fraction of the comet's rotation period, generally just a few hours. This duration proves significantly insufficient to generate the continuous anti-solar jets extending for 1 million kilometers. Maintaining such jets over their entire 1 million kilometer length would necessitate outgassing persisting for days or even weeks, far exceeding what thermal lag alone can explain. Achieving this would require supplementary heat sources, potentially originating from radioactive decay within internal materials or exotic compositions possessing unusual thermal properties. Each added requirement diminishes the model's simplicity and increases its dependence on unverified assumptions. Furthermore, a critical obstacle exists. For this model to produce the observed columnated jets, the geometry must be exceptionally specific. The crater walls would need to be precisely the correct height and angle. The ice deposits would have to be located exactly as required, and the rotation axis would need to align in a particular configuration. Compounding these specific requirements drastically reduces the scenario's probability. While not absolutely impossible, the scenario becomes improbable enough that exploring alternative explanations remains warranted before declaring this mechanism definitively solved. Consider the inherent statistics involved. How many craters would need to possess precisely the correct depth and orientation? How many ice deposits would need to be located exactly where shadowing creates the observed effect? If Comet 3 Atlas possesses dozens of craters of varying sizes and random orientations, what is the probability that several of them coincidentally exhibit the exact geometry required? This probability can be calculated using models simulating crater formation and ice distribution. The answer hinges on assumptions regarding the nucleus's history, its collisional past, the initial incorporation of volatiles, and their subsequent redistribution via sublimation and thermal processing.
All these factors involve significant uncertainty, translating directly into large error bars for any probability estimate. Intuitively, however, demanding multiple coincidences drastically reduces the likelihood. A single, perfectly positioned crater generating one jet seems plausible. Multiple craters, all simultaneously producing jets with the specific observed properties, begins to appear contrived. Furthermore, stability presents a critical consideration. Crater geometry evolves over time as sublimation erodes the surface. Sunlight exposure causes ice to sublimate, potentially altering crater depths, slopes, and shadowing patterns. If the observed jets rely on specific geometric configurations, those configurations might be transient, persisting only for a fleeting fraction of the comet's active lifespan. We are observing Comet 3 Atlas during a distinct evolutionary stage, at a specific solar distance under particular illumination conditions, a single snapshot in time.
This argument regarding selection effects holds merit and constitutes a vital factor in scientific reasoning. Nevertheless, acknowledging selection bias does not negate the imperative to rigorously assess whether proposed natural explanations fully account for the observed phenomena. The crater geometry model currently presents the most robust naturalistic explanation for the clear, unsmeared nature of the jets. It merits serious consideration precisely because it relies solely on established physical principles, incorporates documented behavioral patterns observed in similar celestial bodies, and extends these concepts through reasonable extrapolations validated by other well-studied objects. Furthermore, the model generates specific, testable predictions concerning the potential presence of clumpy structures within the jets. Future observations capable of confirming or refuting these predictions will provide crucial evidence to evaluate the model's validity. This explanation avoids reliance on unconventional hypotheses or phenomena previously unseen in nature. Such parsimony constitutes a significant advantage. However, it also possesses notable limitations, particularly in its difficulty accounting for anti-solar jets and its dependence on specific geometric arrangements within the comet. Whether these shortcomings prove insurmountable or simply necessitate further refinement hinges upon data currently unavailable to researchers. Until high-resolution spectroscopic examinations, comprehensive surface mapping, and detailed analysis of internal clump structures become feasible, the crater model retains viability but remains unverified. It represents one plausible scenario among several, neither conclusively validated nor definitively ruled out, residing within the ambiguous territory science inhabits prior to receiving conclusive evidence. The second natural explanation, falling under the category of fragmentation or ejected fragments, shifts perspective from gaseous outflows to solid particulate matter. Perhaps the observed features stem not from jets of gas, but rather from trails composed of fragments and chunks of material expelled from the comet's core. These solid pieces, themselves undergoing sublimation as they journey away from the nucleus, could potentially generate the visible phenomena. Comets demonstrably experience fragmentation events. They may disintegrate due to tidal forces, thermal stress, rotational instability, or simply because their internal cohesion was inherently poor. If the comet designated 3I Atlas has fragmented into multiple pieces or is currently shedding substantial debris, these fragments could indeed leave conspicuous trails. As they evaporate, they might also entrain and drag along smaller particles with them, enhancing the visibility of the trail.
Early-stage fragmentation debris trails often exhibit remarkably straight trajectories, primarily before the significant effects of orbital mechanics and solar radiation pressure cause the material to disperse.
It remains theoretically possible, yet introducing these specific conditions now actually diminishes its likelihood. The fragmentation hypothesis cannot be entirely ruled out. Certain observed features might plausibly stem from fragment trails. However, as a comprehensive explanation for the fixed jet orientations or the distinct collimation patterns, it proves fundamentally inadequate. This model accounts for some phenomena while simultaneously generating fresh, unresolved questions. Mirroring the crater geometry model, each subsequent refinement aimed at aligning it with observations renders the specific scenario progressively more improbable. We are rapidly depleting straightforward natural explanations, and this situation warrants significant concern given that the alternative interpretations are profoundly complex. Part 6. The technosignature hypothesis. Thrusters, not gas. This proposition fundamentally alters the scientific landscape. It ventures into territory reminiscent of science fiction, yet it is now being seriously debated within peer-reviewed scientific literature by reputable researchers. What if these jets possess no natural origin whatsoever? What if Comet 3I Atlas, designated as 3I Atlas, is not a conventional comet, but rather an engineered artifact, a spacecraft or interstellar probe?
And what we perceive are not gas flows driven by sublimation, but meticulously controlled thruster systems, purposefully maintaining orientation and trajectory throughout interstellar space. Avi Loeb, a prominent Harvard astrophysicist who championed the artificial hypothesis for Oumuamua, has explicitly proposed this very scenario for Comet 3I Atlas, and this time the supporting evidence appears considerably more difficult to dismiss. The central argument, however, is strikingly simple and devastating in its clarity. Should a rotating object possess jets anchored permanently to inertial space, thus resisting any trace of the object's spin, this signifies active compensation for that motion. Such precise control is absent in natural phenomena. Observe how gas vents, rigidly attached to a spinning surface, would invariably trace spiral patterns across their environment. Contrast this with the navigation systems aboard spacecraft. These sophisticated attitude control thrusters possess the capability to execute targeted firings in exact directions, completely independent of the vehicle's rotational state. This functionality establishes a fixed orientation relative to external reference frames, a standard operational feature. This technological approach is neither speculative nor experimental. Humanity routinely implements such systems on satellites and interplanetary probes. Their reaction control subsystems employ precisely directed jets of gas to adjust orientation, ensuring antennas maintain alignment with Earth or solar panels capture sunlight efficiently. The underlying engineering principles are thoroughly understood, rigorously tested, and demonstrably reliable. Consider a hypothetical probe shaped like an eye atlas, possibly cylindrical or ellipsoidal. It might be encased within a protective stratum of ice, serving dual purposes, shielding against cosmic radiation while providing effective camouflage within its surroundings. Beneath this icy layer, flush-mounted onto the surface, are the embedded thrust nozzles. The probe itself may rotate due to residual spin acquired during its construction or launch phase. Alternatively, this rotation could be intentionally sustained to exploit gyroscopic stability during extended voyages through interstellar space. Regardless of the rotational state, the probe's computational navigation system, whatever hardware architecture manages its operations, possesses precise knowledge of its current orientation. It calculates the specific directional thrust required to maintain its intended trajectory or enact necessary course corrections. Consequently, this system orchestrates thruster firings exclusively at the precise moments when the nozzles are correctly aligned relative to the external cosmic framework, irrespective of the probe's continuous surface rotation.
Here is the deeply rephrased text, maintaining the original meaning and length while enhancing readability and flow. The outcome is characteristic jets that remain fixed within an inertial frame of reference. These appear as straight lines projecting from the comet's surface, oriented in specific directions, while the body itself rotates freely beneath them. This model provides an elegant explanation for various observations. It clarifies why the jets do not exhibit spiraling motion. It accounts for their well-defined collimation, their fixed spatial orientations, and their apparent long-term stability. Furthermore, it offers potential explanations for several other puzzling phenomena. The observed non-gravitational acceleration could represent deliberate course correction rather than being attributed to random outgassing. The unusual composition of the jets might indicate engineered propellant distinct from naturally occurring volatile materials. Polarimetry anomalies could stem from artificial dust or exhaust particles possessing properties unlike those of natural cometary grains. Allowing for the possibility of engineering makes all these observations cohere logically. Loeb has proposed that the exhaust velocity generated by such hypothetical thrusters could significantly exceed the approximately 400 meters per second typical of simple sublimation processes. Chemical rockets achieve exhaust velocities measured in several kilometers per second. Ion drives can attain velocities on the order of tens of kilometers per second. If Oumuamua utilizes advanced propulsion, even moderately so by human technological standards, the effective exhaust speed could be an order of magnitude higher than current assumptions. This would imply a substantial reduction in the amount of propellant required to generate the observed thrust and jet characteristics. Consequently, this resolves the mass loss problem that poses difficulties for purely natural explanations. A relatively small fuel reserve could sustain thruster operations for extended periods, potentially years or even decades. Such endurance would be sufficient to navigate throughout a solar system and execute necessary trajectory adjustments. The audacity of the notion might seem staggering at first glance, considering humanity's own ventures into the interstellar void. Probes like Voyager 1 and Voyager 2 currently traverse the cosmos beyond our heliosphere, bearing messages intended for any potential discoverers. They were preceded by Pioneer 10 and Pioneer 11, and joined by New Horizons hurtling onward. If humanity accomplished this feat using technology from the 1970s and early 2000s, It logically follows that a far more advanced civilization could achieve similar feats with superior efficiency. They could dispatch smaller probes equipped with advanced propulsion systems, granting vastly longer operational lifetimes.
Furthermore, if such civilizations were traversing the immense gulfs between stars, employing disguises seems a prudent strategy. Coating their probes with ice, making them appear as mundane cometary or asteroidal bodies would allow them to bypass detection entirely, infiltrating target systems undetected. Naturally, this hypothesis faces significant criticism. Detractors argue it posits alien technology without concrete evidence. It seemingly substitutes one set of unknowns for another. We lack spectroscopic signatures revealing artificial materials. Thermal imaging shows no telltale heat patterns from onboard machinery. There are no detected radio transmissions or laser pulses, the expected beacons of intelligent design. All we possess are subtle anomalies in observed motion and composition, data points that deviate from established natural models. Is this minimal evidence sufficient to draw such a profound conclusion? The central philosophical dilemma remains: at what point does the accumulation of negative evidence, phenomena that stubbornly refuse to conform to natural explanations, transition into positive proof for an alternative, artificial origin? This fundamental debate cannot be resolved solely by gathering more observations. It demands careful judgment, a rigorous weighing of probabilities, and a decisive assessment of how much anomalous weirdness truly transcends the bounds of nature's inherent diversity and variability.
Alternatively, it might represent a derelict probe, tumbling aimlessly after completing its interstellar mission. This hypothesis encountered significant doubt and, at times, outright dismissal within the astronomical community. Proponents of conventional explanations offered alternative, though equally unusual, natural possibilities. Some suggested the object could be experiencing faint hydrogen outgassing, too dim for telescopic detection, yet sufficient to generate the observed thrust. Others proposed it might be a rare nitrogen ice fragment originating from a Pluto-like world orbiting another star. These explanations, while exotic, were rooted in known physics. Further debate surrounded the initial size estimates, with some arguing the object's shape might be less extreme than first thought. This scientific discourse continued for several years, yet it remains inconclusive. Oumuamua itself is no longer observable, accelerating away from our neighborhood and slipping beyond the grasp of even our most powerful telescopes, eliminating any prospect for further direct investigation. The second known interstellar interloper, designated 2I Borisov, however, presents distinct characteristics in crucial respects, setting it apart from the mystery of Oumuamua. Here is the deeply rephrased and polished English version adhering strictly to your requirements. The interstellar object Oumuamua presented no discernible cometary activity during observation. Conversely, Comet 3I Atlas exhibits conspicuous jets and a significant coma. While Oumuamua was only glimpsed briefly near its closest approach to the Sun, Comet 3I Atlas has been tracked continuously for more than 12 months. This extended observation window has yielded substantially more data and allowed for thorough investigation. The artificial hypothesis surrounding Oumuamua primarily stemmed from the absence of expected natural features, what wasn't observed. But the artificial hypothesis concerning Comet 3I Atlas is founded on the presence of features that challenge conventional natural explanations. This represents a scientifically stronger position because positive anomalies are inherently more difficult to dismiss than simple absences. Nevertheless, the parallels between the two objects are striking. Both demonstrate non-gravitational acceleration. Both reveal compositional or structural peculiarities. Both fundamentally challenge established comet models. And critically, both have become central to the same pivotal question: how can we definitively distinguish between extraordinarily rare natural phenomena and potential artificial constructs? The universe is immense and ancient. harboring phenomena entirely unknown to us. It encompasses conditions impossible to replicate in our laboratories and formation environments that remain poorly understood. By their very nature, rare natural events are infrequent occurrences.
We should anticipate moments of genuine surprise, yet there exists a crucial distinction between phenomena that are merely surprising and those deemed impossible, between events that are highly improbable and those exhibiting hallmarks of engineering. Where precisely does one draw that line? The experience with Oumuamua proved instructive. It fundamentally shifted the scientific community's readiness for this very conversation in ways it lacked prior to the year 2017. Consequently, the artificial hypothesis is no longer dismissed outright as absurd. The notion that interstellar objects could be technological probes possesses substantial foundation. Peer-reviewed research exists supported by institutional scientific discussion. NASA itself has sponsored investigations into potential technosignatures, actively pursuing evidence of extraterrestrial technology. Consequently, the question of whether certain interstellar visitors constitute probes has transitioned from fringe speculation into legitimate scientific inquiry. This cultural evolution holds significance. It enables a more objective assessment of candidates like the object 3B Atlas, mitigating the automatic rejection that initially characterized reactions to such theories. We have already engaged in our first formal dialogue concerning interstellar artifacts. This current consideration may represent our second attempt, and crucially, we may approach it with greater analytical rigor this time. Part 8 explores statistical coincidences and cosmic alignments. When anomalies accumulate and peculiarities multiply, probability compels attention. Let us examine the coincidences surrounding 3B Atlas. Considered individually, each detail might seem inconsequential, yet collectively they form a pattern demanding scrutiny. This object did not arrive randomly. Its trajectory traversed the inner solar system, following a path that brought it surprisingly close to multiple planets. Reports indicate approaches near Mars, Venus, and Jupiter during its journey. While no collisions occurred, the proximity of these encounters is statistically noteworthy. For an object arriving on a hyperbolic orbit from interstellar space, possessing effectively random initial conditions, passing near multiple planetary targets seems highly improbable, though not strictly impossible. Further complicating the picture is the object's compositional profile. The James Webb Telescope identified an extraordinary ratio of carbon dioxide to water within its structure. This specific signature, detected with precision, adds another layer to the accumulating evidence warranting deeper investigation.
Even within our own solar system, where planetary formation processes are comparatively well understood, comets primarily composed of carbon dioxide represent a significant rarity. The discovery of such an object arriving from interstellar space, exhibiting this extreme chemical signature, strongly implies it originated in an environment markedly distinct from the conditions typical of standard stellar nurseries. Possibilities include condensation within an exceptionally frigid molecular cloud, perhaps situated at unusual depths, or formation occurring far out in a planetary system possessing an atypical distribution of volatile compounds. These natural explanations remain plausible, yet each specific condition required inherently diminishes the likelihood that this body is merely another arbitrary fragment of ice adrift between the stars. The observations of polarization across the gray and magnolia spectra introduce a further complex dimension. The dust particles within this comet exhibit polarization properties entirely unprecedented, suggesting grain structures fundamentally unlike those cataloged in any known comet, asteroid, or interplanetary dust sample.
while natural processes possess the capacity to generate exotic dust through mechanisms such as radiation processing, chemical alteration, or the presence of unusual mineral compositions, the sheer uniqueness of these observed optical characteristics is striking. We are not merely confronting an unusual specimen, we are observing something demonstrably unique. And true uniqueness, a word that should naturally prompt scientific caution, is inherently rare within the universe, which overwhelmingly favors the emergence of patterns and repetition. Engineered uniqueness, conversely, is an expected outcome. Every technological artifact is, in some specific manner, unique, meticulously designed for a defined function, with materials selected based on performance characteristics rather than their prevalence within natural systems.
If one were meticulously planning a probe's journey through a solar system, deliberate choices regarding orbital parameters would logically optimize scientific observation opportunities or planned encounters. Achieving ecliptic alignment would maximize the likelihood of passing near multiple planets. Strategic timing of perihelion passage could coincide with prime windows for data collection or gravitational assists. Consequently, what might appear suspiciously precise could simply be the expected outcome of such intentional design. Further speculation has emerged linking this phenomenon to the earlier Atlas events, though venturing into this territory demands extreme caution. Some have even drawn connections to the famous OWO signal, a single, intense radio burst detected in 1977 that remains unexplained and never repeated. Could an interstellar probe arriving in 2024 have begun transmitting decades prior from a much greater distance? While the temporal alignment seems improbable and the hypothesis remains tenuous, it exemplifies the human inclination to forge connections when confronted with accumulating unexplained observations. We possess a fundamental drive to seek explanations even when the evidence is elusive.
Human cognition readily identifies patterns once sought, and hypothesizing artificial origins can make each anomaly appear to support it disproportionately. Our minds are not neutral probability calculators. We are inherently drawn to compelling narratives, finding tales of alien probes more captivating than descriptions of peculiar icy bodies. Therefore, safeguarding scientific integrity requires independent verification, multiple convergent lines of evidence, and making testable predictions. We must first determine which specific observations could distinguish between competing hypotheses, and then proceed to make those measurements. Until such decisive data is obtained, the existing statistical correlations remain intriguing and thought-provoking, yet they fall short of providing conclusive evidence. They fundamentally alter the discourse, but fail to resolve the underlying question. This leads us to Part 9. Challenges confronting the technological signature perspective. We must now address the skeptics. Their concerns warrant serious consideration. Dismissing them would constitute intellectual negligence. The most potent objection raised against the artificial hypothesis posits that our observations may capture artifacts inherent to the imaging and interpretive processes rather than reflecting objective physical reality. Stacked, long-exposure images, far from being unprocessed raw data, represent complex composites. These images undergo significant enhancement and combination to reveal extremely faint features undetectable within individual frames. This enhancement process involves critical decisions regarding alignment precision, specific stacking algorithms employed, background subtraction techniques, and contrast adjustment parameters. Different choices in these parameters inevitably yield different visual representations. Could the apparent straight, fixed jets within the coma potentially arise not from genuine structural features, but from specific choices made during the image creation process itself? Furthermore, one must consider the demanding observational conditions. These images were captured using ground-based telescopes positioned near the horizon during twilight. Such circumstances introduce substantial atmospheric distortion due to turbulent air layers and the significant path length light must traverse. To compensate for the comet's faintness, exceptionally long exposure times were required. Consequently, any movement occurring during these extended exposures results in image blurring. Stars typically appear as trails across the frame unless the telescope tracks them with perfect accuracy. Adding to this complexity, the comet itself is in motion relative to the background stars, further challenging the capture of a sharp, representative image.
Choosing what to track when stacking astronomical images fundamentally shapes the final picture, the stars or the comet itself. This critical decision can sometimes generate misleading streaks or jets in the final composite, features that do not exist physically on the celestial body. Some observers interpret these subtle anomalies as genuine comet structures emanating from its core, while skeptics caution that they might simply be artifacts born from the significant technical hurdles inherent in the astrophotography process. Capturing a faint comet presents photographers with complex, often conflicting requirements. Obtaining sufficient light necessitates long exposure times, yet these same long exposures invite celestial motion to disrupt the scene. Our planet's rotation carries the entire observational perspective, causing stars to drift unless precisely counteracted by motorized tracking mounts. Simultaneously, the comet follows its own distinct trajectory against this stellar backdrop. The physical impossibility of perfectly freezing both the rotating Earth's effect and the comet's orbital motion creates an unavoidable compromise. The tension manifests clearly in the image alignment process. When stacking multiple exposures, software must select a reference point for alignment, and this choice directly influences the outcome. Selecting stars as the reference smears the moving comet, while tracking the comet itself leaves trails on the fixed stars. This core dilemma is amplified when combining numerous images. Different computational approaches to stacking further impact the result. Median stacking effectively suppresses random outliers, like impacts from cosmic rays, though it can sometimes blur the comet's finer details. Sigma stacking preserves these subtle structures but inherently amplifies background noise. Sigma clipping methods statistically reject extreme data points. However, this can inadvertently discard legitimate features, mistaking them for noise and creating artificial distortions. Background subtraction techniques attempt to model and remove variations in sky brightness, adding another layer of processing to the astrophotographer's toolkit. Should the processing model error, or if a faint extended structure is misidentified as mere background, genuine features effectively vanish, while spurious ones emerge. Techniques like histogram stretching or unsharp masking, employed to amplify contrast, can expose subtle details, but simultaneously risk exaggerating inherent noise patterns into seemingly significant features. Each processing decision inevitably involves subjective judgment. Consequently, analysts applying different interpretations to identical raw data may produce images that appear profoundly distinct.
Skeptics often cite historical astronomical examples where processing artifacts were mistakenly accepted as genuine phenomena. The intricate network of canals, meticulously charted by Percival Lowell and contemporaries in the late 19th and early 20th centuries, provides a compelling case. These structures were later revealed to be optical illusions arising from the interplay of observing conditions and human pattern recognition, manufacturing non-existent formations where none existed. Spacecraft imagery ultimately dispelled this illusion, revealing Mars as a cratered and arid world devoid of any canals.
Could the jets observed at Enceladus represent a modern parallel? Artifacts that seem tangible within processed images yet might dissolve entirely if we could observe the object more directly using higher resolution or alternative techniques. While this comparison sits uneasily, it is not wholly unjustified. Furthermore, a fundamental question persists regarding the very nature of what we perceive. Jets and cometary tails consist of diverse materials, dust, gas, or ionized plasma, each exhibiting different behaviors. Ionized gas, in particular, can be profoundly influenced by magnetic fields within the solar wind. This interaction can generate structures that appear columnated or fixed relative to external reference frames, rather than dynamically aligned with the rotating nucleus itself. Researchers have proposed that the jets observed emanating from comets might actually consist of ion tails or plasma structures, rather than being composed of neutral gas. If this hypothesis holds true, their orientation would be governed by electromagnetic forces acting upon the charged particles within them. This could naturally explain their fixed alignment relative to the Sun-comet axis, eliminating the need to suggest the presence of artificial propulsion systems. This explanation possesses inherent plausibility, as similar plasma structures have been directly observed originating from other comets. The primary challenge lies in demonstrating conclusively that plasma dynamics alone possess the capacity to generate the specific features precisely matched by these observations. The physics governing cometary plasma remains inherently complex and not yet fully elucidated by scientists. The process begins when ultraviolet radiation emitted from the Sun strikes gas molecules within the comet's diffuse atmosphere, known as the coma. This intense radiation possesses sufficient energy to ionize the molecules, effectively stripping electrons away and producing a population of charged particles, both positive ions and free electrons. These newly formed ions become subject to interaction with the solar wind, a continuous flow of charged particles streaming outward from the Sun.
Embedded within this solar wind are magnetic fields originating from the Sun itself. The critical interaction between the moving ions and these embedded magnetic fields can generate distinctive structures known as ion tails. These tails typically exhibit a remarkably straight and narrow appearance. The magnetic fields exert a constraining influence, dictating the motion of the charged particles and preventing dispersion, unlike dust tails, which follow curved ballistic paths determined by the comet's rotation and orbital mechanics. Consequently, ion tails maintain a fixed orientation specifically aligned away from the Sun, independent of the comet's rotational state. This leads to a compelling possibility. The jets observed on this particular comet could simply be ion tails, viewed from an unusual geometric perspective relative to the observer. Such an interpretation would elegantly account for their observed straightness and fixed orientation without necessitating any exotic or previously unobserved phenomena. However, a significant complication arises with this interpretation. Ion tails are characteristically observed to point directly away from the Sun, yet the images captured on the 8th of November distinctly show jets emanating in multiple directions, including one clearly oriented in the anti-solar direction opposite to the Sun. This multi-directional emission presents a direct challenge to the hypothesis that all observed jets are merely ion tails viewed obliquely. To account for all observed phenomena related to ion tail dynamics, it might be necessary to consider multiple ion populations that respond to varying magnetic field configurations or intricate interactions between the comet's coma and the solar wind, resulting in asymmetric plasma formations. Although this scenario is not implausible, it hinges on specific environmental conditions that may not always be met. To validate this hypothesis, spectroscopic analysis could be instrumental in discerning whether the jets originate from ionized substances or neutral molecules. However, acquiring spectra with adequate spatial resolution to distinguish individual jet characteristics poses a significant technical hurdle. The requisite data to substantiate or challenge the ion tail theory may still be out of reach. Complementing these considerations are thermophysical models. Several studies have employed conventional comet physics to simulate the three-dimensional structure of comets referred to as the 3-eye atlas. These simulations typically start with anisotropic outgassing, where volatile sublimation is localized to specific regions of the comet's surface due to compositional differences or shadowing effects. By meticulously calibrating the placement of active areas and the rotational dynamics, these models have managed to replicate certain instances of non-gravitational acceleration, eschewing the need for exotic mechanisms.
If established physical principles can elucidate the acceleration effects, perhaps they can also clarify the jet formations when the modeling complexity is appropriately managed. The challenge arises from the necessity to introduce sufficient complexity, which often entails incorporating a multitude of free parameters. This proliferation of variables allows a model with 10 adjustable parameters to align closely with nearly any dataset, potentially undermining the model's explanatory power.
Ion propulsion systems, while more efficient, require a continuous supply of electrical power generated by extensive solar panels or nuclear generators. For an object of relatively small size, integrating sufficient power generation capabilities and fuel storage to sustain measurable thrust over several months or even years presents a formidable engineering challenge, though it remains theoretically possible.
However, a critical counterpoint exists: the total lack of definitive proof. Extensive, targeted searches using radio telescopes sensitive to transmissions far weaker than our own have yielded no results. No radio broadcasts, laser bursts, modulated pulses, or any deliberate attempts at communication have been detected. Furthermore, the object's thermal emission spectrum aligns perfectly with that of a warmed surface re-radiating absorbed sunlight, showing no indication of waste heat generated by machinery. Analysis of its visible spectrum reveals absorption and emission lines matching known molecules, specifically carbon dioxide, water vapor, and organic compounds, providing no evidence of exotic propellants or industrial chemicals. Consequently, if this object is indeed a probe, it must be either non-operational, intentionally silent, or employing technology so advanced that its operational signatures remain entirely unrecognized by our current detection methods. Each of these scenarios is conceivable under the artificial hypothesis, yet each simultaneously renders the hypothesis extremely difficult to test empirically. An untestable proposition, however, falls outside the realm of practical scientific inquiry. The persistent silence regarding radio signals particularly strengthens the position of skeptics. Despite dedicated SETI investigations focused on specific areas, no transmissions have been found. If this were a functioning probe actively relaying data to its creators, some form of signal emission would be anticipated. The profound silence, therefore, implies either that the probe is currently not transmitting at all, or that it transmits using methods, potentially involving frequencies, modulation techniques, or physical principles beyond our comprehension that our existing instruments simply cannot perceive. The persistence of the artificial hypothesis, despite its claims, actually undermines its own credibility by demanding increasingly complex supplementary assumptions. Each added premise compounds the inherent improbability of the entire proposition. Consequently, an artificial probe designed to remain completely silent and undetectable by any of our instrumentation gradually loses its distinction from a mundane natural object. When such differentiation becomes impossible, the fundamental necessity for the hypothesis itself comes into question. However, The absence of confirming evidence requires careful interpretation. Our efforts to locate extraterrestrial signals through radio telescopes have inherently been limited, scanning only specific frequency bands over relatively brief intervals. A sophisticated probe could easily evade detection by transmitting only in fleeting, unpredictable bursts, rendering them statistically unlikely to be captured. Furthermore, it might utilize highly focused directional beams, deliberately avoiding Earth, ensuring no radiation reaches our sensors.
Transmission security could be enhanced by encoding signals to mimic natural background noise, effectively camouflaging their artificial origin. Alternatively, the probe might employ a passive strategy, storing collected data internally for retrieval at a later date, or relying on a future return journey to its point of origin, thus transmitting nothing at all during our observation period. Therefore, we cannot definitively conclude that the object is non-transmitting based solely on a handful of unsuccessful searches. We can only state with certainty that we have not detected any transmissions matching our current search parameters, a critical distinction. Skepticism demanding further, concrete evidence remains scientifically justified. As a foundational principle dictates, extraordinary assertions necessitate commensurately extraordinary verification. The proposition that we are observing an extraterrestrial spacecraft certainly qualifies as extraordinary. Yet such extraordinary status does not equate to absolute impossibility, and the lack of positive proof cannot be conflated with definitive proof of non-existence. What we presently possess is a constellation of observational data that presents significant difficulties for conventional natural explanations, while simultaneously falling short of providing conclusive validation for the artificial hypothesis. This state of inconclusive yet intriguing evidence occupies a scientifically uncomfortable territory, where neither definitive acceptance nor dismissal of the extraordinary claim is warranted. True scientific advancement demands greater data collection, more sophisticated analytical models, and a candid evaluation of our current understanding. It necessitates recognizing inherent uncertainty while persisting in investigation. And crucially, it requires resisting the closure of intellectual doors simply because emerging possibilities provoke unease. The progress of science fundamentally relies on sustaining a productive tension. The disciplined demand for robust evidence, coupled with an enduring receptivity to novel concepts. The annals of discovery vividly illustrate both triumphs and errors. We recall instances where prevailing consensus proved fallible, where phenomena categorically dismissed as impossible were subsequently validated, and where the cosmos revealed realities utterly unforeseen. Simultaneously, these records are replete with cases where sensational assertions dissolved under rigorous examination, where unwarranted enthusiasm outpaced demonstrable proof, and where humanity's natural tendency to perceive patterns often attributed significance to random noise. Distinguishing between these divergent paths demands exceptional patience, methodological rigor, and intellectual humility.
We must possess the willingness to entertain the notion that the 3I Atlas signal could be artificial, while concurrently insisting upon the exceptionally high threshold of evidence such a profound conclusion necessitates. This imperative extends to the continuous critique of our own methodologies, the courageous questioning of foundational assumptions, and a perpetual vigilance against the possibility that we might be deceiving ourselves through cognitive bias. Only by embracing skepticism with the same intensity as we pursue curiosity can we aspire to approach objective truth. This leads us to a critical juncture, the implications. If the artificial hypothesis concerning the 3I Atlas signal were accurate, if it represented an engineered artifact, perhaps a probe dispatched by an extraterrestrial civilization to survey our solar system or those beyond, what profound consequences would this revelation entail? Not only for astronomy, but for all of humanity, for our comprehension of our role within the cosmos, and for the inquiries we pose and the futures we envision, the repercussions radiate outward like circles on calm water, extending well beyond the initial discovery. Initially, ponder the nature of the object in question. If it is artificial, as 3I Atlas most probably is, it stands as a reconnaissance probe, an automated explorer dispatched to collect information on stellar systems. This practice mirrors our own endeavors. Our explorers are equipped with tools to gauge magnetic fields, plasma, and cosmic rays. They possess cameras to capture images of planets and moons. They also carry representations of Earth and humanity, such as golden plaques and sound recordings, intended as messages to any potential finders. An advanced civilization would likely adopt similar strategies, albeit with greater sophistication. They would engineer probes capable of autonomous navigation, making necessary course adjustments, enduring long interstellar journeys, and functioning for centuries or even millennia with little maintenance. Equipped with advanced sensors, communication systems, and data storage capabilities, they might program these probes to investigate stars and planets, seeking evidence of life or intelligence, evaluating habitability, and cataloging resources. Alternatively, it could be a dormant relic, the remains of a mission that concluded eons ago or failed during transit. Space is replete with our own silent probes, satellites that have lost power or orientation, missions that surpassed their intended lifespans and fell silent. Interstellar expanse might be similarly cluttered with remnants from innumerable civilizations spanning billions of years.
Its core navigation system could persist in operation even while its scientific instruments lie dormant and its communication arrays fall silent. Effectively, it might become a forgotten ghost ship, adrift within the solar system long after the civilization that sent it has either ceased to exist or simply moved on, leaving its creation to drift unnoticed. This scenario presents a profoundly melancholy thought, yet one not without significant likelihood. History consistently demonstrates that technology often endures long after the civilizations that conceived and built it have faded away. For the scientific community, definitive confirmation of an artificial interstellar object would constitute a paradigm shift, fundamentally altering multiple disciplines practically overnight. Astrobiology would secure its first irrefutable evidence of extraterrestrial technology. The search for extraterrestrial intelligence, or SETI, would undergo a radical transformation, transitioning from solely listening for radio signals towards actively tracking objects within solar orbits, searching for additional visitors from beyond. Planetary defense initiatives would be compelled to broaden their scope considerably, incorporating the possibility of unpredictable behavior from artificial objects alongside traditional natural threats like asteroids and comets. Our established models regarding the prevalence of intelligent life across the galaxy, encapsulated in the famous Drake equation, would demand substantial revision. The existence of even one such probe strongly implies the existence of others. It suggests that civilizations capable of constructing such durable interstellar messengers achieve longevity and technological sophistication sufficient to deploy them. This notion hints that the galaxy might be considerably more populated, more actively explored, and more extensively monitored than humanity has previously assumed. Philosophically, these questions ascend to a deeply profound and unsettling level. If 3I Atlas indeed proves to be an artificial probe, then the answers to its origin become paramount. Who crafted this distant traveler? How vast were the distances it traversed to reach us? And through how many years of solitary flight has it journeyed? Consider that the nearest stellar neighbor, the Alpha Centauri system, lies over 4 light-years away, a journey demanding patience and technology far surpassing our own. With even present-day technological capabilities, a journey to that distant location would require tens of thousands of years. More advanced propulsion systems might shorten the voyage, but the timescales involved remain staggeringly vast. The civilization responsible for 3I Atlas could easily have vanished by now. Their star might have significantly aged. Their planets could have been engulfed or altered beyond recognition.
Their species might have evolved so profoundly that they would seem alien to us, or perhaps they are entirely extinct. We might find ourselves studying the remnants of ghosts, examining a message sent by entities who perished long before humanity first emerged on Earth. But what was the intended purpose? If this constitutes reconnaissance, what exactly were they seeking? The answers could lie in discovering habitable worlds, resource-rich stellar systems, or signs of other technological species. Are we, in turn, being cataloged? Is our solar system being mapped and assessed, much like early explorers charting a previously unknown continent? The possibility provokes both exhilaration and dread. Exhilaration stems from the profound realization that we are not alone, that intelligence has arisen elsewhere in the cosmos and achieved capabilities we ourselves aspire to reach. Dread arises from our complete ignorance of what conclusions they might draw about us, or what subsequent actions such a conclusion might provoke. Human imagination has painted scenarios for first contact ranging from enlightened exchange to catastrophic conflict, yet reality could manifest as either extreme or perhaps something entirely beyond our current comprehension. There remains the critical question of response. If we definitively confirm the artifact's artificial origin, should we attempt communication? Should we try to intercept 3 Atlas, dispatch a mission to rendezvous with it and examine it in detail? 3 Atlas travels at remarkable speed along a hyperbolic trajectory destined to carry it back into the interstellar void within years. Any mission to intercept such an object would require swift design and deployment, a feat that current technological capabilities struggle to achieve. Presently, we lack the spacecraft necessary to quickly adjust their velocity to match that of a fast-moving interstellar entity. By the time such a mission could be organized and launched, 3E Atlas would have long since vanished, retreating beyond Neptune's orbit and ultimately disappearing into the vastness of the Kuiper Belt. In that scenario, our opportunity would have slipped away, perhaps for the best. There exists a perspective within the search for extraterrestrial intelligence, or SETI, community that supports passive observation over active transmission. This cautious approach stems from uncertainty about the nature of other civilizations, their intentions, their technological prowess, and the potential consequences of revealing our own existence. The act of broadcasting our presence could be fraught with danger if the recipients harbor hostile intentions. Should 3E Atlas prove to be a probe, and we engage with it, we would undoubtedly confirm the presence of technological intelligence on Earth, effectively marking our planet on the cosmic map.
While some view this as an opportunity for discovery and contact, others perceive it as a risk that demands serious consideration. These philosophical debates are not novel. However, they gain urgency and relevance when confronted with a tangible object that might be actively monitoring us. From a practical standpoint, if 3I Atlas is indeed artificial, it would stand as one of the most significant observations in human history. The collection of each data point, every spectrum analyzed, and each positional measurement captured would hold immeasurable value, offering unprecedented insight into the potential existence of extraterrestrial intelligence. The pursuit of unraveling the mysteries surrounding the object would necessitate a global orchestration of observations, harnessing the capabilities of every available telescope to scrutinize it across the entire electromagnetic spectrum, from radio waves to gamma rays. Spectroscopic analysis would be imperative to detect any artificial materials or anomalous isotope ratios, offering insights into its composition. Radar observations would play a crucial role in mapping its surface structure, revealing details otherwise inaccessible to conventional telescopic imagery. Furthermore, the search for modulated signals and any patterns within its outgassing could potentially encode information,
hinting at a purposeful design. This ambitious scientific endeavor would not only unite researchers from diverse institutions and nations, but also catalyze an unprecedented collaborative effort to decipher the enigma before us. Yet at the heart of this quest lies the formidable challenge of confirmation. Proving the object's artificiality without physically approaching it and examining its construction details poses a significant hurdle. The standard of proof required for such an extraordinary assertion would need to be exceptionally stringent, a necessity in the face of such a momentous revelation. To sustain this pursuit, we would require a multitude of independent lines of evidence, observations that are reproducible, and models capable of yielding testable predictions. It becomes imperative to exhaustively rule out natural explanations, leaving the artificial hypothesis as the sole viable option. Currently, we are in a realm of anomalies rather than definitive answers, grappling with questions rather than conclusions. The possibility remains that we may never reach a definitive resolution, forever mired in uncertainty, debating possibilities without a conclusive answer due to the object's distance, limited data, and myriad alternative explanations. Despite the daunting nature of this quest, the exercise itself holds inherent value. It pushes the boundaries of scientific inquiry, challenging our understanding of the universe and our place within it.
The pursuit of knowledge, even in the face of uncertainty, serves as a testament to the indomitable spirit of exploration and discovery that defines our species. Even if the object designated as 1I 2017 U1 Oumuamua, commonly referred to as 3 Atlas in this context, is ultimately determined to be a natural celestial body, and even if every observed anomaly eventually receives a conventional scientific explanation, the endeavor itself will have advanced human knowledge. This pursuit will have propelled forward our models of cometary physics, sharpened our comprehension of interstellar objects traversing our cosmic neighborhood, and enhanced our methodologies for discerning between natural phenomena and potential artificial signatures. Crucially, it will have prepared humanity for the eventual day when we encounter something definitively artificial, an occurrence increasingly seen as probable. The galaxy's immense scale and vast age suggest that if intelligence arises and civilizations deploy probes, the likelihood of at least one such probe passing through our solar system over millions of years is not insignificant. 3 Atlas might not be that probe, but the prospect stands that something unmistakably artificial will be detected someday. And when that pivotal moment arrives, it is essential that we are prepared. Meanwhile, another revolution in artificial intelligence is transforming our ability to discover planets orbiting distant stars. While scientists continue to debate the nature of 3 Atlas, a different form of artificial intelligence is fundamentally changing how we find worlds beyond our solar system. In the year 2025, researchers unveiled a groundbreaking study demonstrating how sophisticated machine learning algorithms could detect exoplanets within distorted datasets with extraordinary precision. This development represents more than a minor advancement. It signifies a fundamental shift in the process of astronomical discovery. It marks a transition from reliance on human pattern recognition to large-scale algorithmic data mining, a scale rendered impossible by the limitations of human research teams alone. The pivotal study focused on archival data from the Kepler Space Telescope, the very repository that has already yielded thousands of confirmed exoplanets over the preceding decade. Kepler's planet hunting method involved meticulously tracking the luminosity of countless stars, specifically seeking out minuscule, recurring dimming events.
These dips in brightness occur when a planet transits, passing directly between its star and Earth. Detecting these transits proved exceptionally challenging. The resulting decrease in stellar light, often registering at less than 1%, was frequently obscured by various sources of interference.
Such noise originated from the natural flickering of stars themselves, imperfections in the spacecraft's instruments, cosmic ray impacts, and random statistical fluctuations within the data stream. While human astronomers and conventional computational algorithms achieved significant success in identifying genuine signals amidst this complex background, their capabilities were inherently limited. They could only thoroughly examine a finite number of light curves, the graphical representations of stellar brightness over time. Furthermore, these methods were susceptible to overlooking faint patterns or dismissing anomalous data points that deviated from predicted planetary transit signatures. The sheer magnitude of the Kepler dataset presented a formidable analytical obstacle. The spacecraft maintained an unbroken watch on more than 150,000 stars for a period approaching 4 years. It captured a measurement of each star's brightness every half hour, generating billions of individual data points. Each measurement held the potential, however slim, to contain the telltale signature of a planetary transit, yet was equally likely to be pure noise. The established analytical procedure relied first on automated software algorithms. These programs identified potential transit signals by applying relatively straightforward rules. They flagged instances where a star's brightness dipped below a specific amplitude threshold at regular intervals, consistent with a suspected planet's orbital period. Thousands of these flagged light curves then underwent intense scrutiny by human experts. These specialists visually inspected the curves, attempting to distinguish actual planetary transits from numerous false positives caused by stellar activity or instrumental errors. This labor-intensive process, while functional, was prone to subjectivity and inevitably missed planets whose transit signals were either too faint or too unusual to meet the initial automated criteria. The advent of machine learning techniques offered a transformative solution to these persistent limitations.
This enables them to distinguish genuine, repeating signals indicative of planets from random fluctuations and anomalies, potentially identifying candidate planets that human analysts might miss during manual review. Following the training phase, the models underwent rigorous validation using completely independent test datasets. The outcomes were remarkable. The highest performing model demonstrated astonishing accuracy, correctly classifying light curves as either originating from stars hosting planets or not, with a rate of 99.8%. Understanding the capability of these systems requires insight into the fundamental nature of machine learning. Unlike conventional programming, where developers explicitly code specific rules, machine learning algorithms autonomously discover complex patterns from extensive examples. By processing thousands of labeled light curves, each clearly marked as representing a planet-hosting system or not, the algorithms identify intricate correlations and features statistically associated with each category. Random forest algorithms, specifically, construct numerous decision trees. Each tree functions like a flowchart, posing a series of distinct questions about the light curve data to reach a classification decision. Examples of these questions include: does the light curve exhibit periodic dips in brightness? How pronounced are these dips? Is the dimming pattern symmetrical? How consistent are the dips observed across multiple transit events? Each individual tree asks slightly different sets of questions. The final classification emerges from a consensus mechanism, often described as voting, where the collective responses of all trees determine the ultimate outcome. This ensemble approach significantly enhances robustness,
making the classification resistant to noise and isolated data outliers. Here is the deeply rephrased and enhanced version of the text, adhering to all requirements.
Machine learning, particularly the k-nearest neighbor approach, automatically discovers these intricate relationships, extracting valuable information hidden within the training data that might otherwise remain unnoticed. This represents pattern recognition operating at a level exceeding human intuition. By leveraging immense computational power, it identifies correlations and subtle distinctions imperceptible to the human eye. Achieving this sophisticated level of performance enables machine learning to act as an initial screening filter. It can efficiently scan through millions of light curves, flagging the most promising candidates for subsequent human expert review. Consequently, it becomes possible to identify rare or unusual planets, those possessing orbital periods or radii outside more conventional ranges, without necessitating exhaustive manual inspection of every single star observed. This capability translates directly to a dramatic acceleration in the discovery rate when these techniques are applied to ambitious new surveys like the Transiting Exoplanet Survey satellite, which is monitoring hundreds of thousands of stars across the entire sky.
These could be unique systems where planets exhibit extreme characteristics, possessing very long orbital periods, exceptionally small orbital radii, or orbits that are significantly tilted or eccentric. In such cases, the resulting transit signals become highly irregular and non-standard, often resembling noise or suspected instrumental artifacts. Human analysts examining these light curves might readily dismiss them as mere anomalies, failing to recognize the underlying planetary signature due to their deviation from typical transit patterns.
The overwhelming majority of these objects receive classification as mundane, aligning with established scientific categories. However, rare instances arise where an object exhibits characteristics so unusual it registers as anomalous, displaying unique combinations of properties unseen before within the predictive model. This anomaly flag immediately initiates intensive follow-up procedures. Coordinated observations and meticulous analysis commence. Such a system might illuminate itself like a festive Christmas tree. Unprecedented polarization, extreme carbon dioxide ratios, non-gravitational acceleration, and presently these unsmeared jets would collectively defy expectations. While each individual property might possess a relatively low anomaly score, their specific combination would register off the charts. This same analytical approach holds significant promise for the search for extraterrestrial intelligence. Radio telescopes routinely gather vast quantities of data, systematically scanning across numerous frequencies and sky positions, seeking signals that sharply contrast with the pervasive cosmic background noise. Traditional SETI algorithms primarily search for specific, predefined signal types, narrowband transmissions, pulses exhibiting particular timing patterns, or encoded sequences suggesting deliberate modulation. Yet, what if extraterrestrial transmissions do not conform to our expectations? What if they utilize modulation techniques, frequencies, or coding schemes entirely unforeseen by human design? Machine learning systems, rigorously trained on patterns derived from natural radio sources, including pulses, magnetic bursts, planetary emissions, and similar phenomena, could learn the defining characteristics of authentic astrophysical signals. Such systems would then automatically flag any signal that fails to fit this learned natural profile. These flagged anomalies would emerge as prime candidates warranting investigation for artificial origin. This paradigm shift, moves the search beyond seeking only signals we already know how to recognize, enabling the discovery of signals we previously did not know to seek. Here is the meticulously refined and expanded English narrative, adhering strictly to your requirements. A fascinating possibility exists. Advanced extraterrestrial societies might conceivably employ techniques analogous to our own. Imagine if such civilizations dispatch robotic surveyors to explore distant star systems. These probes could potentially house artificial intelligence systems capable of autonomously analyzing collected data and determining the most promising avenues for further investigation.
Upon arrival in an unexplored stellar environment, a probe might utilize sophisticated machine learning algorithms to categorize planets based on their potential to support life, identify telltale chemical indicators of biological activity within atmospheric readings, and even detect artificial structures or technological signals emanating from indigenous intelligent species inhabiting those worlds. In this context, should an object like 3 Atlas indeed represent such a probe, it might be executing computational processes fundamentally similar to those being pioneered on Earth. These systems could recognize complex patterns and autonomously decide which phenomena warrant closer scrutiny, all without awaiting specific directives from their creators. We might therefore be observing the operational principles of alien artificial intelligence in action, an intelligence meticulously cataloging our solar system, mirroring the manner in which our own intelligence surveys the cosmos beyond. The symmetry inherent in this scenario is profoundly poetic. 2 distinct forms of intelligence, one emergent and biological, the other synthetic and engineered, both driven by the fundamental quest for understanding, both critically dependent on pattern recognition and data analysis, converging across the vastness of interstellar space. Contemplating the essential requirements for such an interstellar journey reveals why autonomy is indispensable. Real-time communication with the probe's creators is utterly impossible. Even traveling at the universal speed limit, light-based signals require years or potentially centuries to traverse the immense gulfs between stars. By the time a probe's query reaches its origin point and instructions are transmitted back, the celestial situation it initially observed would have fundamentally altered. Consequently, the probe must operate with significant autonomy, possessing the intrinsic capability to independently decide where to direct its sensors, what celestial bodies or events to prioritize for observation, and how to appropriately respond to unforeseen circumstances encountered during its mission. Machine learning provides an ideal solution for this complex challenge. By exposing artificial intelligence to millions of simulated cosmic environments, each representing planetary systems with diverse configurations and properties, the system can learn to categorize and rank celestial targets efficiently. When deployed, the probe leverages these computational insights to assess real astronomical systems, discerning which worlds possess atmospheres meriting detailed analysis, identifying moons with potential subsurface oceans, and evaluating orbital arrangements that indicate long-term stability or chaotic evolution. This intelligent prioritization optimizes the probe's constrained operational window, directing its instruments toward observations offering the greatest scientific return.
Furthermore, if the mission involves seeking evidence of advanced civilizations, the AI must detect technological signatures despite lacking prior knowledge of their specific characteristics. Through training on natural cosmic phenomena, the system learns to identify anomalies, unusual patterns defying conventional astrophysical explanations. These could include atmospheric chemistries hinting at industrial-scale pollution, unexplained luminosity fluctuations suggesting artificial illumination, unnaturally ordered radio signals, or infrared emissions consistent with waste heat from massive energy production. Crucially, the probe need not comprehend the cultural or biological nature of any civilization it encounters. Its function is solely to recognize deviations from natural processes, flagging systems exhibiting artificial characteristics for further investigation. If the 3i Atlas probe operates under this methodology, it may have already analyzed Earth's system, recognizing our radio transmissions, elevated atmospheric oxygen levels, and urban illumination patterns as compelling indicators of technology. The scenario could involve preparing a comprehensive report, gathering data to send back home once circumstances permit, or retaining it in memory for transmission should a return become possible. The intersection between human artificial intelligence and the hypothetical existence of alien artificial intelligence opens up intriguing prospects for communication. If both parties employ machine learning for recognizing patterns, there could emerge a common framework, a shared mathematical foundation that surpasses the boundaries of species and culture. Neural networks, decision trees, Bayesian inference, these are not mere human inventions, but outcomes of information theory and probability. Any civilization grappling with noisy data and incomplete information may develop analogous tools. This commonality could foster understanding despite vast disparities in biology, chemistry, and history. Although we might not share a common language or mathematical notation, we could share the fundamental logic of extracting signal from noise, classifying, predicting, and learning from examples. This shared logic might serve as the cornerstone of first contact, a mutual acknowledgement that both parties are addressing similar challenges with similar methodologies. Time Door 5. Part 12. Breakthrough in Dark Matter Detection. While astronomers keep vigil over the skies for interstellar visitors, physicists are pursuing something even more enigmatic within laboratories situated deep underground. Dark matter, the elusive substance constituting roughly 85% of the matter in the universe, has yet to be directly observed, despite decades of relentless searching.
Here is the deeply rephrased and enriched English text, adhering strictly to the original meaning and facts, while enhancing flow and detail. Astronomical observations provide compelling evidence for the existence of dark matter, despite the absence of direct detection. The rotational velocities of galaxies exceed what their visible components could possibly sustain, implying the presence of additional, unseen gravitational mass. Furthermore, the gravitational lensing effect observed within galaxy clusters bends the light from more distant objects to a degree that cannot be explained by the visible matter alone. The specific patterns detected within the cosmic microwave background radiation also necessitate the influence of dark matter for a complete explanation. Nevertheless, physicists have yet to directly observe a single dark matter particle interacting with ordinary matter. No collision with a detector has ever been recorded, and the fundamental properties of these elusive particles remain unmeasured, until potentially very recently.
From humble beginnings as compact tabletop instruments in the 1980s, the quest to directly detect dark matter has evolved into constructing immense multi-ton detectors filled with liquefied xenon. These sophisticated instruments are now buried deep within vast caverns, thousands of meters below the Earth's surface. This profound depth serves a critical purpose, shielding the sensitive equipment from the constant barrage of cosmic rays that would otherwise overwhelm any potential dark matter signal. Globally, major collaborations like the renowned Lux-Zeppelin experiment and the Panda X detector in China have pushed the boundaries of sensitivity to astonishing degrees. Their designs allow them to register interactions so extraordinarily rare that observing even a single event might require years of continuous monitoring. Despite this exceptional sensitivity and the painstaking elimination of backgrounds to levels previously deemed almost unimaginable, the detectors remain profoundly silent. No definitive signals from weakly interacting massive particles have emerged. While these null results cannot definitively prove that WIMPs do not exist, they deliver powerful constraints, dramatically narrowing down the possible locations and properties where such particles could be lurking. The vast parameter space within which dark matter might reside is steadily contracting, and with it, the previously held confidence that our initial search strategies were perfectly aligned begins to waver. A promising new approach, utilizing a technology called superconducting nanowire single-photon detectors, fundamentally changes the experimental paradigm. Rather than relying solely on waiting for dark matter particles to collide directly with atomic nuclei, this method hunts for incredibly faint flashes of light. These photons could result from dark matter interacting with electrons within the detector material, or even being produced through subtle quantum mechanical processes. The SNSPD itself is a marvel of precision engineering, consisting of ultra-thin, superconducting nanowires chilled to temperatures just a fraction above absolute zero. The underlying physics is elegantly straightforward. When a single photon strikes the nanowire, it momentarily disrupts its perfect superconducting state. This tiny disturbance generates a measurable electrical pulse. This technology achieves sensitivity at the quantum limit, capable of detecting the arrival of individual photons. Consequently, it can register interactions that would be utterly invisible to conventional dark matter detectors, opening an entirely new window onto a potential dark matter signature.
At exceedingly low temperatures, specific materials exhibit a phenomenon known as superconductivity, wherein they lose all electrical resistance, thereby permitting the flow of electric current without any dissipation. This superconducting state is quite fragile, maintained through a delicate equilibrium of quantum mechanical factors. If a single photon impinges upon a minute area of the superconducting wire, it can deliver sufficient energy to disrupt this equilibrium momentarily. As a result, superconductivity ceases locally in that region, leading to a sudden emergence of resistance. The alteration in the current can be discerned with remarkable precision. Subsequently, the wire reverts to its supercooled state and superconductivity is restored, thereby enabling the detector to reset itself and become prepared for the detection of the subsequent photon. This cycle can be repeated an astronomical number of times each second, rendering superconducting nanowire single-photon detectors exceptionally swift and effective in counting photons. For the purpose of identifying dark matter, it's crucial to understand that hypothesized ultralight dark matter particles might manifest as photons when they interact with standard matter. Numerous theoretical frameworks propose this notion. For instance, axions, a widely considered dark matter candidate, are theorized to transform into photons when subjected to robust magnetic fields. Other ultralight particles might stimulate electrons within atoms, leading to photon emission as the electrons descend to lower energy levels. These photon signals would be exceedingly faint, consisting of individual photons that arrive sporadically, concealed amidst background noise arising from thermal radiation, radioactive decay, cosmic radiation, as well as instrumental artifacts. However, with adequate shielding, cryogenic cooling, and meticulous analytical techniques, SNSPDs could potentially identify these signals, discerning patterns indicative of dark matter as opposed to random background noise. The recent technological advance now enables the exploration of previously inaccessible territory below the 1 MeV threshold. This entire low-mass domain, essentially untouched by prior investigations, stands open for scientific inquiry. Theoretical frameworks propose dark matter might manifest across an astonishing spectrum of masses, ranging from incredibly light axions, particles vastly less massive than electrons, to immense primordial black holes. While experimental efforts concentrated for decades within the intermediate WIMP window, consistent null results have prompted a crucial reassessment. Expanding the search to include ultralight candidates provides entirely new hunting grounds. The SNSPB detector facilitates this exploration, offering fresh possibilities and the significant prospect of discovery within a regime previously unexamined.
This strategic shift is not unprecedented. The quest for dark matter has demonstrated adaptability throughout its history, consistently pivoting towards novel approaches when dominant theories failed to yield results. In the 1990s, the scientific community anticipated WIMPs would be detected within a decade. Frustratingly, this prediction proved incorrect, catalyzing increased attention toward alternative candidates. These included axions, sterile neutrinos, primordial black holes, self-interacting dark matter, and asymmetric dark matter, among others. As experiments progressively eliminated simpler possibilities, the inventory of plausible candidates has steadily expanded. Some physicists express frustration with this process, questioning whether 4 decades of unsuccessful searches imply a fundamental misunderstanding of gravity or cosmology itself. Others view this systematic exploration of parameter space, actively ruling out unworkable possibilities, as an essential and healthy facet of the scientific method, persisting until only the underlying truth remains. The single photon source detector approach aligns with a particular philosophical outlook, one that ventures into uncharted territories to uncover what lies hidden. There is a subtle yet profound connection between this method and the 3 Atlas project. Both endeavors seek out phenomena that defy conventional models, compelling us to broaden our categories and expectations. Dark matter challenges our perceptions of what constitutes matter, while an artificial interstellar object questions our understanding of natural processes in astronomy. Each requires us to interrogate our assumptions, to entertain possibilities that may seem unconventional but could well be true. Moreover, both exemplify the pivotal role of technology in facilitating discovery. Just as advanced detectors aid in the identification of dark matter candidates, improved telescopic and imaging technologies reveal anomalies in cometary behavior. Progress is consistently propelled by the development of instruments capable of perceiving what was previously imperceptible. This invisibility may stem from faintness, subtlety, or merely a lack of direction in our search. There is also a symmetry in methodology. Dark matter hunters craft experiments to discern signal from noise, seeking patterns that distinguish themselves from the background. Researchers at 3 Atlas analyze images and spectra for features that deviate from anticipated norms. Both disciplines confront the challenge of false positives, signals that appear intriguing but are later revealed to be instrumental artifacts or statistical anomalies. Both necessitate extraordinary patience, often dedicating years or decades to projects that may yield no findings. Ultimately, both hinge on the same foundational principle.
Nature manifests most profoundly through anomalies, deviations from established theory, moments where observation stubbornly resists prediction. Such discrepancies compel a choice: refine the theoretical framework or unveil something previously unknown. Beyond this rigorous path lies a more speculative contemplation, residing firmly within science fiction's domain, yet impossible to entirely dismiss. If elusive dark matter particles exist and possess even the faintest interaction with ordinary matter, could sophisticated extraterrestrial societies master their manipulation? Could they potentially harness dark matter as an ultimate energy source, employ it for revolutionary propulsion systems, or integrate it into technologies utterly beyond our current imagination? If a certain hypothetical object, such as the 3I Atlas, were artificial and employed exotic propulsion, might that propulsion fundamentally rely on physics transcending our present understanding, possibly incorporating interactions with dark matter? This remains pure speculation, untethered from empirical evidence, yet it powerfully illustrates a fundamental principle. Expanding our grasp within one scientific domain invariably illuminates new possibilities in others. Each breakthrough in physics reshapes our conception of what technological achievement, natural or artificial, might be feasible.
And crucially, when seeking to identify artificial constructs within the cosmos, comprehending the absolute boundaries of physically possible technology becomes critically important. Consider the immense energy density associated with dark matter. It permeates all of space, filling the voids both surrounding celestial bodies like Earth and existing within their very structure. Imagine the potential if a civilization could successfully extract usable energy from this ubiquitous reservoir. This would grant access to a fuel source existing intrinsically throughout the universe, eliminating the burdensome requirement to transport conventional propellants. A spacecraft equipped with such technology could continuously harvest dark matter particles from its immediate cosmic environment and convert them directly into thrust. This capability would enable sustained acceleration over interstellar distances, fundamentally transforming the prospects of deep space exploration.
Nevertheless, the concept highlights the potential advantages available to civilizations possessing a profoundly advanced grasp of physical laws, capabilities entirely beyond our present comprehension. Furthermore, dark matter might serve purposes extending beyond mere propulsion. It could potentially act as a medium for concealment. If sufficiently advanced technology allowed manipulation of dark matter fields, it might be possible to shield an object from electromagnetic detection. This could involve bending light around the object or absorbing radiation in specific ways, rendering it invisible to both optical and infrared telescopes. An interstellar probe equipped with such dark matter stealth technology could observe a distant solar system undetected. It could gather comprehensive data regarding planets, potential biosignatures, and even technological civilizations, all without revealing its own presence. Our instruments scanning this system would register no anomalies, while this hidden observer meticulously cataloged everything about the civilization it studied. This scenario may seem speculative, yet it aligns logically with principles observed in contemporary defense systems, where stealth technology and avoidance of enemy sensors are paramount strategic concerns. Why would an advanced civilization exploring potentially hostile or unpredictable stellar environments refrain from employing similar precautions? The necessity for concealment becomes a rational consideration when probing unknown territories. The very inability to detect dark matter might reveal something profoundly significant about the boundaries of observation. It suggests the universe may harbor phenomena interacting solely through gravity, devoid of electromagnetic signatures. Entire structures, objects, and potentially even civilizations could exist, leaving their only discernible mark as faint ripples in space-time. We would remain perpetually ignorant of their true nature, confined to deducing their presence solely from gravitational effects, forever denied direct sight, touch, or measurement. This realization is deeply humbling. It implies our cosmic map, constructed entirely from electromagnetic phenomena and gravitational clues, likely overlooks immense swaths of reality. If this perspective holds, then our certainty regarding what constitutes the natural order versus artificial constructs, what is feasible versus impossible, must be tempered by the profound understanding that we perceive merely a fraction of existence. Meanwhile, technological progress continues to illuminate this hidden universe. The James Webb Space Telescope persistently redefines astronomical understanding with every observation campaign.
In 2025, one of its most remarkable achievements was the direct imaging of a Saturn-mass exoplanet, TWI-7b, orbiting a young stellar body 32 light-years distant from Earth.
Directly photographing exoplanets presents extraordinary challenges. These worlds are vanishingly small and incredibly dim compared to their intense host stars, akin to attempting to capture an image of a firefly glowing beside a searchlight viewed from across a vast desert. The majority of known exoplanets have been discovered indirectly, identified by the subtle gravitational tug they exert on their star, or the minute dimming of starlight as they pass in front of it. Using the James Webb Space Telescope to view the planet itself, resolving it as a distinct point of light, requires blocking the star's glare with a coronagraph and having sufficient angular resolution to separate planet from star. JWST can achieve this, and TWIAS-b is one of the least massive planets ever directly imaged. The planet sits within a debris disk, a ring of dust and rocky material orbiting the young star. JWST's infrared vision revealed not just one ring, but 3 distinct structures, concentric bands of material separated by gaps. These gaps are likely carved by planets whose gravity shepherds dust and debris into organized patterns. TWIAS-b itself appears to be sculpting some of this structure, clearing a path through the disk as it orbits. The images are stunning, showing detail that would have been impossible before JWST, revealing planetary system architecture in the process of formation. This is not an ancient, settled system like our own. This is a system still being born, still dynamically evolving, planets and debris interacting in ways that will determine the final configuration billions of years from now. Why does this matter for 3I Atlas? Because planetary formation is where objects like comets come from. In our solar system, comets are debris from the outer regions, icy bodies that never got incorporated into planets, leftovers from the construction project that built the worlds we know. When we observe young systems like TW Hydrae, we see those construction sites directly.
3I Atlas likely originated within such a disk orbiting a distant star, billions or millions of years ago, under conditions we can only deduce from its present characteristics. However, this observation leads to deeper speculation. If comets inherently form within debris disks, and if civilizations emerge within some planetary systems, could some of these civilizations deliberately deploy probes within their own debris disks, cleverly disguised as natural objects? A probe encased in ice would visually mimic a comet. Positioned within the disk and receiving a subtle nudge, it could be ejected by planetary interactions alongside naturally formed comets. This would send it on an interstellar trajectory appearing entirely ordinary. To other civilizations observing that system from the outside, the probe would be indistinguishable from naturally ejected debris. This strategy would constitute perfect camouflage, allowing the probe to hide in plain sight among thousands or even millions of similar-looking objects. Therefore, if this method of concealment proves effective and such camouflaged probes are widespread, then a fraction of the interstellar objects traversing any given system might be artificial in origin. Not all, and perhaps not even the majority, but some certainly could be. And 3I Atlas might very well be one of them. JWST's capability to observe planetary systems as they form provides crucial insight into the prevalence of different system architectures. Understanding whether certain configurations are uncommon holds direct significance. If we determine that particular arrangements are rare and recognize that the 3I Atlas origin system needed to be rare in a specific manner to achieve its distinctive composition, this knowledge directly influences probability models. Conversely, if we discover that diverse chemistries and complex protoplanetary disks are widespread, then natural interstellar objects possessing uncommon characteristics should be more numerous, rendering 3I Atlas less exceptional. Every advancement in our knowledge of planet formation refines our expectations of what natural interstellar visitors should resemble. This established baseline is fundamental for identifying anomalies, as one cannot recognize something unusual without a clear understanding of what constitutes the norm. JWST is systematically cataloging these norms across hundreds of systems, constructing a robust statistical foundation. This will eventually allow us to state with confidence whether objects like 3I Atlas fall within the expected parameters or represent genuine outliers requiring explanation. Progress in quantum communication represents another frontier. Achieving entanglement in space marks a significant step.
As humanity develops communication technologies that would appear fantastical to previous generations, a specific milestone was reached in 2025. China's quantum microsatellite Jinan-1 successfully demonstrated real-time quantum key distribution between the satellite and multiple ground stations separated by continents. This achievement brings concepts once confined to science fiction progressively closer to reality. Such a network would link multiple ground stations and orbital nodes, enabling secure communication channels that could fundamentally transform sectors like financial transactions, military coordination, and personal data privacy, forming the backbone of a future quantum internet. The potential link to probes like 3A Atlas and the search for technosignatures, while inherently speculative, offers captivating possibilities. If humanity is developing quantum communication for unhackable transmissions, it is plausible that advanced extraterrestrial civilizations possess even more sophisticated iterations. An artificial probe employing such technology could encode its transmissions within quantum states. This data would be transmitted back to its originators using methods virtually impervious to interception or unauthorized decryption, requiring specific knowledge of the underlying protocols to interpret. Traditional SETI searches focus on detecting modulated electromagnetic carrier waves, deliberate patterns within radio signals that suggest intelligence. Quantum transmissions, however, would lack these recognizable signatures. Instead, they would manifest as seemingly random noise, indistinguishable from natural cosmic radiation for any observer lacking the precise decoding techniques. Consequently, we might already be surrounded by alien quantum communications, completely unaware of their presence, as we perceive them merely as background static. This scenario introduces a concerning implication for detection efforts. As human civilization rapidly advances towards utilizing quantum communications and other exotic signaling methods, the period during which civilizations emit detectable radio signals might become remarkably brief. Our own technological trajectory could render the traditional radio window for discovery fleeting, potentially obscuring the very signals we seek from other intelligent life. Here is the refined English narrative, preserving all original meaning while enhancing readability and flow. Early technological development typically involves methods that are both inefficient and readily detectable. As civilizations advance, their technological approaches become significantly more efficient and substantially harder to detect remotely. This progression creates a critical challenge for SETI, search for extraterrestrial intelligence. If most civilizations transition rapidly through the radio phase, potentially spending only a few centuries developing radio technology before advancing to superior methods, the opportunities for detection shrink dramatically. We would face the daunting task of intercepting signals during an extremely narrow temporal window. Alternatively, we must pioneer detection systems capable of identifying signals from far more advanced technologies that currently elude our recognition. Consider the hypothetical 3E Atlas probe.
If it operates as an interstellar messenger, it might broadcast continuously, using techniques entirely alien to our present capabilities. In effect, it could be transmitting powerful signals that we are fundamentally incapable of perceiving.
However, emerging quantum technologies offer promising countermeasures. The development of quantum radar or quantum sensing techniques might allow us to identify faint quantum signatures that betray the presence of artificial structures or devices. Quantum states, inherently fragile, decohere rapidly in warm, noisy environments. Natural celestial bodies existing at typical cometary temperatures would therefore exhibit no quantum coherence. Yet, if the 3I Atlas incorporated superconducting circuits or other specialized low-temperature quantum devices, these systems could potentially maintain coherence. Such persistent quantum states might generate detectable signatures, provided we knew precisely what to observe and possessed the necessary sophisticated instruments. While this scenario remains highly speculative, bordering on aspirational, it powerfully illustrates a fundamental principle. Breakthroughs in our own technological capabilities continuously unveil novel strategies for identifying artificial phenomena previously invisible to us. Each new capability we acquire effectively expands the universe of potential artificial signals and objects we can recognize. Part 15. Planetary Defense and Interstellar Exploration, a New Era. The identification of 3 IU Atlas-class interstellar bodies and the extensive study they have inspired represent a pivotal moment in humanity's approach to objects traversing the cosmic expanse between stars. Prior to the 2017 observation of Oumuamua, such visitors remained theoretical concepts, entities whose existence was mathematically plausible, yet never empirically confirmed. Having now verified 3 examples within a decade, scientists infer that interstellar objects likely traverse the inner solar system with surprising frequency, potentially numbering several annually. However, their detection remains limited due to their faintness or the insufficient sensitivity of existing survey systems. As global telescope networks evolve, survey initiatives expand, and artificial intelligence-driven detection algorithms refine their capabilities, the rate of discovery is poised to surge. Each newly identified visitor will offer critical insights into the vast diversity of celestial bodies drifting through the galaxy. This evolving understanding carries profound implications for planetary defense systems. Traditionally, these initiatives, such as NASA's Planetary Defense Coordination Office, have concentrated on cataloging near-Earth asteroids and comets, performing precise orbital calculations, and assessing impact probabilities decades in advance.
They coordinate international observational efforts and devise strategies for intercepting or neutralizing threats before they endanger terrestrial populations. While historically focused solely on solar system-bound hazards, the recognition of interstellar objects as potential cosmic travelers necessitates an expansion of these protocols. The integration of interstellar bodies into planetary defense frameworks marks a significant adaptation, ensuring humanity remains prepared for threats originating beyond our celestial neighborhood. Stable or periodic orbits offer predictable paths for celestial objects, allowing for reliable tracking. However, interstellar visitors fundamentally alter these calculations. Arriving unexpectedly along non-repeating hyperbolic trajectories, they enter our domain with minimal prior warning. By the time detection occurs, these objects are frequently already traversing the inner solar system. This provides observers with a severely limited window, often only a matter of months, to gather meaningful data before they depart permanently. Consequently, planetary defense frameworks must broaden their operational scope significantly. This necessitates a critical upgrade in early warning capabilities. Detection systems need to become substantially faster and more sensitive, capable of identifying interstellar objects at greater distances from the Sun. This increased range is paramount. It grants humanity precious additional time to formulate an effective response. Furthermore, characterization protocols must be primed for instantaneous deployment following any detection event. Coordinated global efforts are essential involving telescopes worldwide working in unison to collect diverse datasets, spectroscopy, photometry, polarimetry, radar observations, maximizing scientific yield before the object escapes beyond our reach of instruments. Response strategies also require reevaluation. While impact mitigation remains a core objective, plans must now encompass both the immense scientific opportunity presented by these rare visitors and the potential for deliberate intercept missions should an object display unusual characteristics or heightened interest. The example of Oumuamua 3 Atlas demonstrated that interstellar guests can possess incalculable scientific value, offering unprecedented glimpses into the physical conditions and processes prevailing in other star systems. Failing to capitalize on such opportunities due to inadequate preparation would indeed constitute a profound scientific tragedy. Achieving this level of preparedness demands unprecedented international coordination. Collaborative structures are already emerging to address this challenge.
The International Astronomical Union has established formal protocols governing the announcement of new discoveries and the sharing of observational data. Major space agencies, including NASA, the European Space Agency, the Japan Aerospace Exploration Agency, and others, work together systematically on tracking these objects and conducting their detailed characterization. Amateur astronomer networks supply observational data that significantly supplements the work of professional observatories. These contributors often fill critical gaps in coverage, providing essential information precisely when official facilities are unavailable. However, the current system remains fundamentally unstructured. Each newly discovered object is treated as an isolated incident rather than an element within a coordinated scientific initiative. Moving beyond this reactive model requires deliberate structural reform. Experts increasingly agree on the necessity for formalized frameworks, dedicated financial resources, and pre-established response procedures. The concept of pre-positioned missions capable of rapid deployment warrants serious consideration, particularly if a truly remarkable interstellar object enters our solar system. As our technological capabilities advance, the ethical and profound existential implications become increasingly pressing. A definitive confirmation that an interstellar visitor possesses artificial origins would present humanity with unprecedented challenges. Initiating an interception mission could be interpreted in starkly contrasting ways. To some, it might represent a bold act of communication, a deliberate signal announcing our presence and technological prowess. Conversely, others would view it as a potential act of aggression involving interference with another entity's property or mission objectives. Currently, humanity lacks concrete protocols to guide such a scenario. There are no established international agreements detailing how to respond to confirmed technological signatures from beyond Earth. While the United Nations Office for Outer Space Affairs has engaged in theoretical discussions about these complex issues, academic debates transform into urgent, real-world decisions when faced with an actual object traversing our solar system. The fundamental questions demand immediate resolution. Should we attempt communication? Should we proceed with discrete observation? Or would deliberate ignorance be the safest course? Different segments of global society would undoubtedly arrive at divergent conclusions regarding the appropriate path forward.
Here is the deeply reworked and refined version of the text, maintaining all original facts and meaning while enhancing flow, detail, and suitability for narration, with numbers expressed in words. The fundamental challenge lies in capability versus intention. Even if humanity possessed the desire to intercept the object known as 3I Atlas, could we actually achieve it? This object traverses space at interstellar velocities, moving tens of kilometers per second relative to our Sun. Achieving the necessary matching velocity demands colossal quantities of propellant and energy, far exceeding the capabilities of any existing spacecraft. Such a mission would require years of gravity assists and intricate orbital maneuvers just to catch up, assuming it were possible at all. By the time we could theoretically design, construct, and launch an intercept mission, 3I Atlas would already be lost beyond the orbit of Neptune. It would vanish into the vast, icy wilderness of the outer solar system, an area Voyager 1 has only recently begun to approach. While future interstellar objects might be detected earlier, offering more time, the engineering hurdles remain profound. We would need spacecraft equipped with propulsion systems far more advanced than those currently available, technologies ranging from nuclear thermal rockets to even more speculative systems capable of rapid acceleration and achieving the high delta-V required for such a pursuit. Though these advanced propulsion concepts exist within laboratories and theoretical research papers, translating them into operational spacecraft is a decades-long endeavor. Consequently, perhaps the most viable answer is not interception, but rather preparation. Rather than chasing objects only after they are discovered, the strategy could shift to positioning observational assets within the outer solar system itself. Deploying satellites or telescopes into distant orbits, these assets would act as sentinels, scanning for incoming interstellar visitors long before they reach the inner planets. Early detection from such a vantage point could provide humanity with years of warning instead of mere months. This extended time frame would be crucial, allowing ample time to mobilize global resources, coordinate sophisticated observations across multiple platforms, and potentially launch intercept missions with a significantly higher probability of success. The proposition demands substantial financial commitment, involving the deployment of sophisticated instruments into distant orbits that require years to reach and pose significant maintenance challenges. Yet, if one entertains the possibility that interstellar visitors could comprise artificial probes and genuinely considers the prospect of learning from or even communicating with such entities, the expenditure becomes justified.
The potential reward, possible contact with extraterrestrial technology or intelligence, far surpasses the considerable cost. Whether the object known as Oumuamua proves to be natural or artificial, it has already fundamentally altered the discourse. Astronomers now seriously entertain the notion that some interstellar objects might function as probes. Consequently, scientists engaged in the search for extraterrestrial intelligence now incorporate the search for physical artifacts into their strategies, extending beyond the mere detection of radio signals. Funding bodies have recognized the legitimacy of technosignature science, acknowledging it as a field worthy of support. The long-standing reluctance within professional astronomical circles to discuss potential alien visitation has noticeably diminished. This shift did not occur because conclusive evidence emerged, but rather because the scientific community has learned that maintaining an open mind does not necessitate relinquishing rigorous standards. Investigators can rigorously examine anomalies without succumbing to unwarranted belief. They can entertain the possibility of artificial origins without prematurely endorsing it. This intellectual flexibility, this readiness to consider unsettling alternatives while steadfastly demanding robust proof, represents the essential process by which science navigates into uncharted and uncertain domains. The territory ahead remains profoundly uncertain. Humanity stands poised on a threshold, gazing outward into a universe we have only just begun to explore, detecting objects whose true nature remains largely speculative. As our telescopic technology advances and our survey initiatives broaden over the coming decades and centuries, we will undoubtedly discover additional interstellar visitors. Some of these entities will be readily identifiable as natural phenomena, fragments of ice and rock propelled from distant solar systems by planetary interactions. Others will present a puzzle, exhibiting anomalies that challenge our current understanding. There is even the possibility that some may be artificial, deliberate creations of civilizations that have mastered space travel millions or even billions of years ago, sending out their emissaries to explore the universe. We inhabit an epoch where these inquiries are transitioning from philosophical musings to concrete scientific endeavors. The realm of what we ponder is becoming subject to empirical testing and observation. This transformative period marks a new chapter in our pursuit of knowledge, where speculation is increasingly grounded in evidence, and the quest for answers is guided by rigorous scientific method. This pivotal transition stands as a historic moment. Future historians, regardless of their nature, could well reflect upon the initial decades of the 21st century as the epoch when humanity genuinely commenced its search for cosmic neighbors. It marked the shift from merely contemplating the question, "Are we alone?" to actively pursuing answers. The object designated Oumuamua is an integral part of this narrative. Whether it ultimately proves to be an unusual comet or something inherently artificial, this enigmatic visitor has propelled humanity to re-examine established assumptions, refine existing astronomical models, and develop novel techniques for distinguishing naturally occurring phenomena from potential artificial signatures. It has demonstrated that the boundary between these categories is not always clear-cut, revealing that nature possesses a capacity for weirdness sufficient to imitate design. Recognizing genuine design, therefore, demands more than mere intuition. It requires sophisticated analysis and discernment. This encounter has instilled profound humility, reminding us of the vastness of our ignorance concerning the diversity of objects drifting between the stars. It underscores how much more remains to be learned about the possibilities inherent in nature or artificiality within a universe far stranger and more complex than we currently envision. Consequently, as Oumuamua continues its outward trajectory, accelerating into the outer solar system and eventually returning to the realm of interstellar space, we maintain our vigil. We observe, we measure, we engage in rigorous debate, and we remain in a state of profound wonder.
This sense of wonder is the fundamental engine driving discovery, and discovery is the process that transforms wonder into tangible knowledge. Somewhere amongst the billions of stars within this galaxy and the trillions beyond, there may exist other beings wondering upon the same profound questions, observing their own interstellar visitors and asking whether they are alone. Should Oumuamua indeed be artificial, it signifies that such civilizations have already uncovered the answer to that age-old query.